Welcome to the second episode of the FORCESPRO demo series on active suspension control. In this video, we will show you how to implement the active vehicle suspension control using the FORCESPRO QP solver. In the previous episode, we discussed the modeling details of vehicle dynamics and preview information. Now, we will try to transform that problem into a model predictive control form suitable for FORCESPRO. Considering that we have linear system dynamics, this is clearly a linear MPC problem with a quadratic objective function and a terminal cost term. We also have lower and upper bounds on each of the four control inputs. In terms of runtime parameters, the initial state and preview information are changed at each sampling instant. Furthermore, we have to define a parametric additive term G containing preview information at each stage. Considering the QP nature of the problem and the need for stage-wise parametric terms for preview information, the low-level interface of FORCESPRO is a suitable option. It supports quadratically constrained QPs and provides full flexibility for defining multistage MPC problems. Let us now introduce the basic MPC problem data. We start off with state space matrices A, B, C, and D defined as follows. Next, we define the problem dimensions, specifically 6 state variables and 4 control inputs. We also define 20 as the length of the prediction horizon, which is also going to be equal to the length of the preview horizon. Finally, we prescribe the cost factors in the quadratic objective function, as well as the lower and upper bounds on control inputs. We will use the multistage MPC form of the low-level interface to define the parametric additive terms containing preview information at each stage. For that purpose, we will introduce pre-n_omega as the name of the additive term gn at stage n. During runtime, the preview information will be mapped to these parameters. Let us now define the stages struct needed for code generation. We first define the multistage problem with n equals 20 stages for the whole prediction and preview horizon. Then, for each stage, we define problem dimensions comprising the number of stage variables, equality constraints, and lower and upper bound decision variables. Next, we define the quadratic and linear stage cost terms in the objective, with the linear term being set to 0. The lower and upper bounds and control inputs are defined by prescribing the indices of those variables within the decision vector, followed by the actual values of the upper and lower limit. Equality constraints capture the system dynamics and are comprised of previous introduced state space matrices. Finally, we define parameters that will be provided as preview information at runtime. Once the stages and parameter structs of the problem have been defined, we can generate the solver and obtain a highly optimized, custom-tailored C code by calling the generate code command. This will generate the appropriate QP solver and download the necessary C code libraries to our host machine. The downloaded files will hold the name vehicle_mpc_ with preview according to the above set code option. We can now simulate the model by running it in a for loop and calling the generated solver at each time step. For that, we must define the problem struct with all of the runtime parameters. In this case, it will consist of initial conditions and preview information for the whole horizon. Now we can run the solver. By obtaining the optimal control actions for the next time step, we can promptly update the state vector and thus the preview information for that time step before rerunning the solver. The acceleration results clearly show the improvement in performance coming from active vehicle suspension, as it substantially reduces vertical dynamics and improves riding comfort. This can be seen in the figures, with blue curves, which represent vehicle suspension with preview, having lower oscillations and faster dynamics. As a result, active suspension control leads to lower maximum acceleration and less time required to regulate the acceleration back to 0. By looking at the control actions of each wheel individually, we can observe that the front right part of the vehicle body lifts as soon as the bump is in sight of the preview sensor. This occurs at time mark 0.3 seconds, which is 0.5 seconds, that is a full length of the preview horizon, before the front right wheel hits the bump at time 0.8 seconds. Such action improves shock absorption and therefore reduces acceleration. This completes the implementation part of this demo. In the next video, we will look into the actual code script and show you how to run the FORCESPRO QP general solver and this example on your machine.